Okay, so it's week 7, and I like this little tradition. Tim wrote a problem on the board, and is it the same math that you just did is it the math that covers the panel that you guys just built at SpawnCon?
Yep.
Okay, super.
Those are the dimensions for it.
Yeah.
And I just emailed you the pictures of it.
Yeah, I thought I'd just go ahead and bring those up since you showed them. Courses. Actually, I put it under conferences. 2015, SpawnCon. There's one of them. What's the why does the bottom look kind of white? Is that just a cloud reflection?
No.
Or is that something?
Yeah, that's clouds.
That's just glare reflection. Yeah. Interesting. Okay.
I thought you were talking about the base. I'm like, well, they put it up on a wheeled platform that was white. So.
Oh. And you guys got an honorable mention, but no cash prize. Is that kind of what it came down to?
It wasn't artsy enough.
It's just too sleek and elegant. Yeah, not
it was too functional.
not kitschy enough. Apparently.
Yeah.
You were also saying that the judges neglected to actually feel the heat, the functionality. Yeah. That's too bad.
Every single person that came to look at it put their hand up there behind the duct to feel the heat coming out. I'm like, oh man, that's amazing.
Yeah.
The judges, I'm like, put your hand behind this, you can feel, the heat. None of it.
Maybe it's more. Yeah, I didn't look at the criteria, but it sounds like it was more aesthetic rather than functional. I guess if this was a energy technology competition, I think we probably would have done better. That's not what it was. I saw people making little, miniature libraries and I don't know, just like furniture kind of things.
Outdoor libraries. Outdoor libraries. There was half a dozen of the. Let's put a sink and stuff and a countertop to roll out next to your barbecue grill.
Okay.
But there was like no holding tank. There was no source of water for the sink or anywhere for the sink to drain to. Like, well, that's kind of weird. Why do you even have that?
Looking for aesthetics, that was the
But I thought the barbecue grills were pretty functional and not really aesthetic.
Yeah.
Did one of the barbecue grills end up winning or?
Yeah.
Oh.
All of them, I think.
Oh, yeah.
Huh.
That turntable one.
They were pretty sweet.
Yeah.
That turntable was really sweet.
Yeah.
Okay. So tell me the problem that you've written up there, Tim.
Okay, so our solar panel that we built for SpawnCon 15, the dimensions are 42 inches by 60 inches. If solar insolation is 1,000 watts per square meter, how many watts was our solar panel?
Oh, okay. All right, so this is pretty straightforward. So
Where'd you find the conversion for the inch squared to meter squared?
Just pull it up on Google, but you can find it back here.
It's in the back, right?
And yeah, if you want to write down that conversion, 1 square inch is 0.000645 meters squared.
yeah, so just to reiterate, basically what Tim's asking is what is the how powerful is this solar thermal converter? So all I've done here is written down the two numbers. It's 42 inches wide, 60 inches tall. We can see that from the figure. So 5 feet tall, 3.5 feet wide. What was the tubing you used there in the middle?
It's gutter downspout, aluminum gutter downspout.
Okay, so that does not have the baffles like you would in the soda can
Correct.
style.
It has headers at both ends though.
Okay,
With a
so
7/8 inch hole.
okay, 7/8 inch hole on the top, so you get a little more residence time than you would if you didn't have anything. Okay. So, do you want to go ahead and just solve it on the board then, Tim, and then I'll follow along, and then I'll give another version too. So what's the thought process here?
So you guys work me through it. Is there anything in this problem right off the bat? Is there anything there that's not information that I need?
No, you need all of it.
Need all that?
Yeah.
Okay, everything there we know that we need. So we're gonna pull out our dimensions. So we have 42 by 60, and that's in inches. But what's our final answer need to be in?
Meters, watts.
We need to come up, well, yeah, eventually we're getting to watts, but our conversion we know is square meters. So somehow I need to get from inches to square meters. So how do I do that? What's the first thing I need to find?
The total area in inches.
Yeah, let's find total area first, right? So how do I find the area of that? Length times width, right? So it's just gonna be 42 times 60. And what do you come up with?
2,520
2520? And that's
square inches.
square inches. Okay, so how, but now we know we need to get it to square meters because of our conversion, right? How do I get that to square meters? I've got a conversion factor up here, right? So I just take my 2520 and do what with it? With my conversion factor? Multiply it times that conversion factor, which is 0.000645 meters squared. And what do I come up with? 1.6254.
Correct. That's square meters.
And that's square meters. Okay. That's, now we know the area. So how do we figure out how many watts that is? What can I do with that number to find out how many watts it is? Multiply it times 1,000.
So just
Watts
moving the
per-
decimal point 3 places to the right, right?
Watts per square meter. My square meters cancel out. And yeah, 1,625
0.4,
watts. Yeah, 0.4. So 1,625.4 watts. We said, you know what, that's not a really easy number to use, so we just wrote down about 1,600 watts, which is pretty accurate. And right after we wrote that down, we had a guy who's an engineer come up and say, hey, how'd you come up with that? So I got to sit down with the Sharpie on a piece of plywood and write out the equation for him and show him how I got from point A to point B. So it's a pretty honest question and something pretty typical that you might run into.
Where'd you get the insulation value of 1,000 watts per meter?
Straight out of your textbook, that's standard. It varies on time of day and where you're at and what the atmosphere looks like and what the air density is and yeah. But that's pretty much the given standard is 1,000 watts per square meter.
Yeah. So let me just review what Tim went through, and I'll do this one more time. And I think today I'm going to use Microsoft Excel and pull a few other things together. The last few times I've kind of written it out in one kind of long equation, like kind of one big fraction. But what I did first of all was just kind of reiterate what Tim did on the board. So I first calculated area by multiplying height times width. I've got 42 inches times 60. Looks like meters squared should be inches squared. Let me just fix that. So 42 inches times 60 inches.
Yep.
60 inches
Or you just go-
gives me 2520 inches squared. And then this is the conversion. You know, it's in your textbooks. There's lots of units conversions out there, but there are .0000645 square meters in 1 square inch. Turn that around, it's something like 1,600. But at the end of the day, that panel, now, did you, for your calculation, Tim, did you use just this part inside the frame? Did you use the whole frame? What fraction did you use?
The part inside the frame.
Okay.
The part of the actual, inside the frame, there's a 2x4 frame all the way around this. So I measured the inside dimensions of the framework.
Yeah.
Which is our black area.
Did you include the header? Did you include the two manifolds as well?
Yes.
Okay. So, and he did include the top and bottom manifolds. So basically anything that you see in black here was included.
Inside the solar, yeah.
Yeah, inside the solar. So the frame itself was not. That's reflective, and so you're not going to get any energy harvesting. And then the other question came up. So I ended up with 1.6 square meters. I only have two significant digits there. That's fine for the purpose of this calculation. The other question is, where did this 1,000 watts per square meter come from? That is the standard insulation value for sunlight. So you can see again, with watts per square meter, we multiply by square meters, you come up with a 1,600 watt system. And if you remember from some of our previous discussions, about a kilowatt is what an American household consumes in electricity on average, kind of running all of your electrical appliances. So you can kind of look at that and say, well, gosh, if I could turn all of that heat into electricity, and we'll get to that later, you can't really, you could power your house. But it's already heat, and of a house's energy profile at this latitude, approximately using about 5 times as much energy in heat than you do in electricity. So 5 of these, granted running at the appropriate times, 24/7, et cetera, would be enough to heat a house on average. Would it work on a day when it's cold and dark? No. But that's just kind of a ballpark way of thinking about how powerful something like this is. 4 or 5 of them, if running nonstop, could take care on average of a house. So.
You can see where it was partly cloudy there, and it varied between 120 degrees of output when the clouds were covering it, and 180 degrees when it was getting direct sunshine.
Oh, so you're seeing as high as 180 Fahrenheit? Yeah. Yeah. And we can get into the heat transfer a little bit more. It's also important that you know the distinction between temperature and heat. Heat measures energy, and temperature is more or less energy density when it comes right down to it. Temperature is more or less how much energy there is per molecule, really, when it comes right down to it. So we can dig into the physics of that more later. But let me show you, and this will be a good warm-up for when you get into your summary 3 for this class. I want to take this problem and just play around with it a little bit in Microsoft Excel. So let me get a new blank workbook going. So I'm going to close my other one out here. Get a new one. Okay. So I'm going to work in just a column format. So I'm going to take the same numbers that were just there. I'm going to put the units on it so we can keep track of that. Also, and this is looking forward beyond summary 3, this is looking forward all the way to ETE 214, which is a course that you'll take more than likely in your final semester during your degree program. So this will get you started on that too. So I'll put a little row in for height, and I'll put that in inches. And I'll put a little row in for width, and I'll put that in inches. And then I'll put another one in for area, and I'll put it in inches squared. then another one for area in meters squared. And then I'm going to put in that solar constant. I'm going to call it phi. And I'm going to put the units in, watts per meter squared. And then I'm going to put in power. I'm just going to put that in watts. So I've just kind of laid out the skeleton of the program using Microsoft Excel. I've written them down in a column rather than a row. It's kind of the transposition of where we were before. We were writing everything out in one big row. It's tough to do that in Microsoft Excel just because the way the columns and rows are shaped, but it doesn't matter. When you read a book, you're reading from left to right and from top to bottom. So we're still working from top to bottom. We're still working in a conventional direction. I'm also going to get a little bit fancy in here and superscript that. And I got into that box just by using Control 1. So I'm going to put a superscript on this too. Control 1, superscript, boom. Same deal here, watts per square meter. Control 1, superscript, done. Okay. So we were at 60 inches high, 42 wide, and it's important that you put the units in the cell there. So you're not guessing, trying to remember or whatever. It's just sitting right there in front of you. Now, obviously, the area just equals that number times this number. And I'm going to insert something here. Another thing that's sometimes handy is to highlight in yellow or whatever your favorite color is, the cells that you're entering information into. I'm also going to go back 000645. 645. This is going to be meters squared per inch squared. Oh, good question. I'll show you here. Superscript. Superscript.
You mentioned a 4 there?
Yeah, let me do a Control 1. So if I go back in a number, I can set the number of digits. So there, it didn't know what I typed in. There was a number, and it defaulted to some general category, which did not have enough memory allocated to display all the digits. Now it does.
They usually do it in money. Most people use Excel for money,
Mm-hmm.
so it only has two
No,
decimals.
what I
That's the
meant is
default.
in the actual conversion in the book, it says 6.452.
Oh,
I was just wondering
you're asking why I didn't use that one?
why we dropped that too.
Okay, so the question is, why did I not choose to use more significant digits when they're at my disposal? I have 5 in front of me, and I guess the book has 4. When the device was built, I've got 2 significant digits on each of the 2 dimensions. 42 has 2 significant digits. 60 also has 2 significant digits. We'll run the calculation with the 3 that I used, and we'll run it again with 4, and we'll see how big the difference is. And I think it'll be clear then why I did not use the 2. Yeah, we'll be able to quantify it. It's a great question, and we'll do it. We'll actually do the calculation and see. Okay, and a lot of times on a conversion, and this is just my convention, use whatever you like, I just call it blue. Like, it came from out of the blue. So to get area, square meters, we'll multiply that by this. There we go. And I also know phi, and I'll change that to symbol. Phi, that's the solar constant, watts per square meter. I'm going to type that in as 1,000, and that's also a blue constant. And then to get the power, this is just going to equal the area times power density. Control 1, number. Use a comma, sure, fine, okay.
The one thing I'll add on that really helps is have a color code for your calculations as well. That's the ones that the blocks that have formulas. I'd usually use green.
Oh, yeah. That's a good question. So I can do that here. Maybe, this guy, you'd say you highlight wherever you actually have a formula?
If I have a formula.
You give it a
it's
special one?
green,
Yeah,
mine.
okay. And again, yes, Tim uses green, I just selected gray here, but, so now you kind of can quickly see which cells you would enter information into. So, someone comes along with, well, gosh, how much power if I double the height? Well, go ahead and put 120 in there, and it tells you right away. It's all sitting
And if
there.
you want to neaten it up, the other thing you do is put up at the top, put a guide, an index up there, that yellow is my inputs,
There we go.
blue is my constants, and gray is my calculations.
Yeah, good idea on that. And just say, input, calc, and const. Something like that.
Yep.
Yeah, pretty
And that
simple.
way, anybody looking at your spreadsheet knows exactly what's what.
Yeah. So the question came up, let's just go ahead and answer it straightforwardly. Why not add that fourth significant digit? Well, no. Yeah, you put it on there. Now, if we can see the difference, we can have equals this, equals, let's just see what
You didn't put
percentage we
that,
were
so I
wrong.
rounded it up to 20,
Yeah,
to 26.
so I'll take that number, subtract it from that number, and then divide it by this number again. I'll put that as a percentage. And so I was off by 0.03%, so three parts in 10,000. And even this number right there itself, that's only one significant digit,
You have to
so,
have a meter.
Yeah.
That's constantly variable, that changes by the second, so.
yeah.
So once you get to where you got 6 digits, the 7th one is pretty much unneeded.
More or less in any engineering discipline that you're ever going to encounter, 3 significant digits is plenty.
Okay.
Carrying that fourth one around, it bought us a little bit, but who's ever going to remember, oh, was it a 1625 or a 1626? No, it's a 1.6 kilowatt system. So,
Then you have to figure, you'd also figure, it's like, okay, what are the variations of my tape measure versus your tape measure? And is the wood warped a little bit? Is that truly perfectly square?
yeah.
So those little things are
Those,
not.
they are in fact insignificant. They are not significant digits. Okay, well, that's a good remote problem. I will take a quick pause and then we'll get back into the rest of the class.